Hey, welcome everyone to my video about subset sum for dynamic programming. In this video, I'm going to try to discuss the subset sum problem, and I know that there's a lot of videos already about this topic, but I don't feel that any of them do justice on how to actually approach the problem. They just directly give the solution and there you go. But I don't think a lot of them actually say, here's why we need to choose dynamic programming, here's how to approach it, here's the pseudocode, and here's the actual code. So I'm going to attempt to do this in this video. So let's begin. Hopefully you've heard of the subset sum problem, which I'll just abbreviate as the SS problem. But if you haven't heard of the SS problem, very basically, it's a very famous problem in that our input is essentially, it's a list. Let's just call our list A. So I'll just say input is list A, and I'll make it more specific with items 1 to n. So essentially there's n items in list A, and we're also given a target B. Okay, and what we want to output is true if we can form a subset of A which adds up to B, false if we cannot. So basically an example of this is, let's say I give you A equal to something like 135 or 134, and B is equal to something like, so B, remember B is just a number, B is the number, actually let's add in one more thing, let's add in the 2 here, let's say B is the number 5, okay, then this will actually return true, and the reason for that is we can do 3 plus 2, or we can do 1 plus 4, and they both equal 5, and what I want to do in this problem is that if it does add up to B, then also return this subset. Okay, so very basically that's the problem. We want to break it down into a subset, see if we can reach a certain target, and if we can, return that target. Otherwise, we can't, so we return false. So now that I've discussed the problem, I want to discuss why we want to choose dynamic programming versus anything else. Now, if you've never heard of dynamic programming before, maybe the first thing you might think about is, so actually let me just label this. So this is part 1. So why dynamic programming? So if you've never heard about dynamic programming before, then you might just directly want to do something like a brute force approach. Now, what is brute force? Brute force in this case is considering every single subset of A. And we know that if I'm given a list and it has n elements, then it has a total of 2 to the n subsets. So this is actually going to be theta of 2 to the n. And this is very, very bad. And it's essentially just going to take forever to run. So this is why we don't want to do it this way. You don't want to consider every single 2 to the n subset and see if any of them adds up to B. And I'm actually not sure if this is theta or omega. I think it's omega. But anyways, we're not going to do this approach. It just takes too long and it's horribly inefficient. Another approach you might think about is recursion. Well, when you want to think of recursion, you have to think about, how can I make this problem smaller? Can I make this problem smaller? And the answer of that question is actually yes. Now, the thing about recursion and dynamic programming is that they're correlated. If you can write something using dynamic programming, you can write it using recursion, and vice versa. So if you can think of something using a recursive approach, then you can definitely write it using dynamic programming. So what would happen in recursion here? Remember, in recursion, we want to make our problem smaller each recursive call. So we know that we don't want to do the brute force because it's simply going to take forever to do. So now we think about recursion. Can we do it recursion? And a little thought will actually say yes. And the reason for that is, look at the inputs that we're given. We're given A and we're given B. I can definitely make these smaller. For example, instead of considering the entire list, I can consider maybe half of it. Instead of considering B, which might be a number like 10, I might consider a number like 8 or 7. It's still making it smaller. So that's how we can use recursion. Essentially, whenever you can still use when you can still make your problem smaller, then you want to think about recursion. And if you're dealing with dynamic programming, then dynamic programming might be better than recursion, just because you save a lot of memory this way. So now that we've discussed why to actually do dynamic programming, let's talk about how to approach the problem. And I think this is the spot that most videos lack in, is that they don't tell you how to approach it. They just directly say dynamic programming and this is what we're going to do. But in this video I actually want to tell you how we're going to approach this problem, but this is actually going to apply for any generic problem. Okay, so how do we approach it? So the first thing you actually want to do is consider backwards. So what do I mean by this? So what I mean is, assume that we are given a subset S that adds up to B. Okay, so assume we have the answer. Assume the program's run and we have the answer. What I want to try to do is I want to basically try to think of a recursive structure to this. How can I make this smaller? And then I'm going to implement it. So this is actually the common solution to also a recursive problem. Essentially what you do is you assume that you have the solution in the end, and then you try to think of a property or something that you see in the structure that you can make it smaller and smaller. So that's actually going to help you do your recursion. So here, assume we are given a subset S that adds up to B. Now, let's say S is something like 1 to n. Now, I don't mean to say that the S contains the number 1, the number 2, and the number n. I'm just saying here that an S contains about n items. Here's the first item, here's the second item, here's the nth item. I'm not saying that in S we have the number 1 or the number n. That's not what I'm saying. So it's very important to understand that this is just saying that S contains the first item, the second item, all the way to the nth item. Okay? So now that we have this, now we have to ask ourselves something. How can I make this smaller? Well, if we're given a subset S here, then I can directly think of two ways that we can make it smaller. The first way is, let's say this element n, so let's just call this I. Let's say n, and then this is why I had this right over here, is not in the set S. If it's not in the set S, then what does this mean? Well, then it means that S is equal to 1 to n minus 1. And again, this means that it contains elements, the first element all the way to the n minus 1th element. It doesn't say that it's number 1 and then number n minus 1. So if the nth element is not in the set, then we can say that the set contains element 1 through n minus 1. So now you have to ask yourself, does this make the problem smaller? And the answer to this is yes, it does make it smaller. How is it making it smaller? Well, initially we start off with 1 to n. Now we have 1 to n minus 1. So if I have this, what can I say? What I can say is the following. I can say that now S 1 to n minus 1 is a subset of elements that adds up to B, right? Because here we see that this was elements 1 to n that add up to B. Now I say that n is not in the set, so now S is equal to 1 to n minus 1 elements, and then S1 to n minus 1 is a set of elements that adds up to B. So that's one case. What about the other case? The other case is a little bit more trickier, but it follows the same approach. N is in the set S. Now what can I say here? Now if I were to write something like S is equal to 1 to n, well, this is essentially just this problem right over here. So what I'm going to actually think about is another way of writing this, and this is the way I want to write it. I want to say S is equal to some S prime union, this is my union symbol, the nth elements, right? So we have a S prime, and then we're going to add on the nth element. This is how I'm going to think about it. Now I want to be able to say something about this S prime, because I want this S prime to be smaller than S, and I want to essentially say something about the S prime, so I can get some sort of recursive substructure. So what can I say about the S prime? Well, let's think a little bit about what the S prime actually is. So the S prime is just a set. So it's a subset of elements. How many elements are there? Well, there's 1 to n minus 1 elements, because this is the nth element. So subset S prime has elements 1 to n minus 1 of elements 1 to n minus 1. Now here is where most people get confused. We're not done parts 1 and 2. There's still something to add on to this. And can you think of what it might be? This is kind of true. S prime is a subset of elements of of 1 to n minus 1. But look at the initial definition that we had. Assume that we are given a subset S that adds up to B. Does this thing right over here add up to B? We say that if n is not in the set, then S 1 to n minus 1 does indeed add up to B. But if I'm saying that S is in the set, then S prime with elements 1 to n minus 1 does not add up to B. It actually adds up to B minus an. Now think about this very carefully. Why is this the correct way with sum? B minus an. And I'm actually going to put capital B here. So since n is in the set, then we know that elements 1 to n add up to B. But if I'm just considering elements 1 to n minus 1, then the sum is excluding the last element, is excluding the nth element, an. So that's why the sum over here is B, which is the sum we want, minus an. Now that we've discussed parts 1, 2, there's still something we have to add on to part 3. Now, as with all recursive or dynamic programming problems, we want to think about some sort of predicate, and the predicate is essentially the problems that we're trying to solve. Now, the problem that I'm trying to solve is the following. L, and then ij is equal to, now what do I want these ij to actually be? So I want I to represent the items. So this is the nth minus 1 item, this is the nth item, like that, and I want the j to represent the sum. So what I can say here is L of ij is equal to true if there exists a subset S which contains items 1 to I with sum j. False if there is not such a subset. And just to be crystal clear on what these two actually mean, our value of I is going to range from 0 to n, and our value of j is going to range from 0 to b. So what is this actually saying here is the following. The ith element, so let's say I is something like 5. Does there exist a subset with elements, the first element all the way to the fifth element, with some j? And let's say j is something like 8. So how you can essentially read this is, so if you have something like I, 5, 8, then we can say true if there exists a subset with 5 elements that has sum 8. That's essentially how you would read it. Now you might be thinking, why do I have this I and j and why I don't just have an I? Like, how did I know what to put here? And this is essentially what this is going to be telling me. As you can see in the first case over here, I don't know anything about the sum. All I know is that if n is not in the subset, then I can just consider a smaller size. So that's where I got the I from. It is the second case right over here that I see that if I'm considering a smaller size, I also have to be considering the sum. I can see that the sum is also getting smaller here. So that's why I also added something with the sum right over here. So this is our definition, or predicate, whatever you would like to call it. And just looking at this, what do you think the answer to our original problem would be? So answer to original problem. This is simply just going to be L at what? Well, how many items do we want? Well, at maximum, we might have all n items, the nth item. Now, what would the sum be? The sum we want is b. So again, how you can read this is equal to true if there exists a subset with n elements that has sum b, like that. So note that up here we kind of wrote a little bit of recursive definition, but now I really want to write it formally so we can actually understand how to write the dynamic programming part to this. So we have our predicate right over here. Now with every recursive programming or dynamic programming question, you essentially want to write a predicate and boil it down so we can very easily write the code for it. So now let's think of the predicate that we're going to be writing, or the answer to the predicate. So we have L of I and j. Now let's think about our base cases. Firstly, usually in recursive programs or dynamic programs, essentially what you want to do is, if you have a certain amount of variables, you want to try setting them to 0 and seeing what they give you. So what happens if I is equal to 0? Well, if I is equal to 0, then what does this mean? This means that basically there's 0 items in the subset. So if there's 0 items in the subset, then can there exist anything with a sum j? Well, the answer to that is false, right? Because if there's 0 items, then I can't really create any sum other than the 0 sum itself. So the answer to this is actually going to be false. Similarly, let's consider if we have j equals 0. Now, if j equals 0, what does this mean? It means that the sum is 0. Now, is it possible for the sum to be 0 and for this predicate to still return true? Well, the answer to that is actually, if you think about it, it's going to be yes. When can the sum be 0? Well, the sum can be 0 when basically there's no items. If we're not returning anything, if there's nothing to be added into the list or into the set, then the sum is going to be 0. So then this right over here is going to be equal to true. So I'm just going to format this properly. Now we've considered our two base cases. Now let's just say this is otherwise. So if I does not equal 0 and j does not equal 0, then what? Well, then this is where we have our recursive definition right here help us. It's either going to be this case or it's going to be this case. So what we're going to write over here is L, and watch it, I'm just following this. So this is going to be n minus 1 or I minus 1, and the sum j is going to remain the same, or it's going to be L. What do I have here? N minus 1, so I minus 1. But the sum here is going to be b minus a of n. So it's going to be j minus a. It's a I, which is actually equal to ai. So why am I considering actually this right over here instead of the sum b? Remember, we're treating it as smaller subproblem. So when I'm right here, this is the sum that I'm actually going after. I'm not going after the big sum. I'm going after this sum right over here. So this is essentially a recursive definition that we can now write in terms of dynamic programming. So now that we've considered all three parts right over here, the discussing the problem, YDP, and how to approach, now we're actually going to be starting to write the pseudocode. And to write the pseudocode, this is essentially all we needed right over here, because this is essentially the recursive definition. So now let's write the pseudocode. So we have the subset sum problem, which I'll abbreviate to SS. What does it take in? It takes in an array A, which has n elements, and it takes in a sum B. Now what do I want to do? Well, the first thing here is you want to address the base cases. The first thing I'm going to do is address this true base case. So now look what happens here. J is equal to 0, so I'm actually going to be looping over the i's. So for I equals 0 to n, do. So what is it going to be? L I 0 is equal to true. Right? Again, think about what this means. This is saying that I'm going to be looping over each individual I, and when the j is 0, j is a sum. When the sum is 0, then it's definitely possible for me to make sum 0, because I'm just not going to include any items essentially. That's the true case. Now let's address the false case. So for j is equal to 0 to, this time it's going to be to b, because remember, j goes from 0 to b, do. We're going to write L at 0 to j is equal to false. Again, what is this saying? This is saying that if we have 0 items, if there's like nothing inside, then regardless of the sum I'm creating, I can't create it. Now you might be thinking that like, if you have 0 items, you can still create this 0 sum, and you're right, that's already taken care of in this case right over here, so we don't really need to write a special case for that. So now that we have those two out of the way, now we essentially need to write the main one. So now the main one goes as follows. So for I is equal to 1 to n, do. Again, I already considered I 0, so I'm just starting, I already considered 0, so I'm just starting at 1. I already considered 0 here, so again, I'm going to start at 1. For j equals 1 to b, do. Now what am I going to do here? Essentially, all I'm going to do is I'm going to say L at I j is equal to the following. It's equal to L at I minus 1j, or it's equal to I minus 1, j minus a of I. And if any of these are true, then this will mean that we will be able to create a subset, or we will be able to create a subset with the ith item, or I items, and the sum of j. Now you could kind of make this a little bit better, and in that what you can actually put here is the following. You could put if j minus a at I is less than 0, then, well, what does this mean? Well, then I of L of ij is just going to be equal to this. The reason for that is if the ith element, and then we minus it from our, this is essentially like our capacity or our sum. If it's less than 0, then essentially this means that I can't add this into my list, or the capacity is going to be, or the sum is going to be essentially negative. I can't add it. So to alleviate that, I'm just going to be considering this case. This case is essentially not possible right over here. So this is just another way of writing it. Else, this case right over here is the correct one. So this is essentially our pseudocode that we have. Here's the first base case, the true base case, here's the false base case, and here is what we did right over here. Okay, so now that we have this out of the way, now I actually want to see if we can actually return something if it does exist. So the first thing I'm going to check to see is, does it indeed exist? And remember, what is the answer to our original problem? The answer to our original problem is NB. So what I'm going to check to see is if L at NB, if this is true, then essentially what I can do is here I can find the subset. Now how am I going to find the subset? Well, essentially when you want to find the subset, you want to work in reverse. This is going to create a table for us. Here we're going to start at the edge essentially, and then we're going to work our way backwards, and we're going to figure out what the items in the subset are. So how we're going to do that is, so I'm going to set m equal to n, and I'm going to set this variable b is equal to capital B, and I'm going to set this element s is equal to essentially an empty set. So this is essentially going to basically help us loop backwards the entire way. How I'm going to do this is the following way. So while b is greater than 0, do. So while the sum is greater than 0, I want to keep going backwards. I'm going to check to see if L at m minus 1 b. So if this is true, then essentially what this means is that this case right over here is true. So I don't actually have to add the element that I want to add right now. I can just go backwards. So what I'm going to write here is I'm going to say m is equal to m minus 1, m minus 1. What I'm going to write next is the subset, the s, essentially doesn't change at all, and the b doesn't change at all. I don't really have to write these, so I'm just going to remove them. The other case is this case right over here. This case was false, so this case must be true. So what we're going to see here is m is equal to m minus 1. Definitely, we see that it's going down. The b, actually let's do the s. What is the s equal to? S is equal to s plus, well, it's going to be adding this element right over here. So I'm going to be adding the m element, and the value of b is going to be b minus this element right over here. I'm literally just copying this word for word. So we have, this is essentially our b right over here. As you can see, it decreases by ai, it decreases by am, and I'm essentially going to be adding this element to the subset, because I know that if I'm right here, then we are in this case, case 2, in which n is in the subset. And then let's just do, we will just do something like print s. And that's it. Finally, what we can do is we can return L at n b. We don't really need to return this, but we can return this anyways. So this is our answer, and if it's true, then we're going to print the subset. So now I'm going to give you a chance to look at this, and then I'm going to write the actual code in Python. Alright, so now I have a Python file open. Let's just essentially very quickly write this. So I'm going to define my subset. So here I'm going to write subset, and it's going to be taking a list A and a sum B. Now, the first thing I'm going to do is I'm just going to say n is equal to the length of my list. Okay, now I need to declare my 2D list. Essentially here, it's our Lij. So I need to declare Lij, and what I'm just going to call it is L. Now L is equal to, so this is just a shorthand for me to do it. Let me just say none for I in range, B plus 1. Don't really worry about what I'm doing here. I'm just essentially just declaring the list. And here it's going to equal for I in range n plus 1. So this is like my n by b list. So once that is completed, what I need to do now is handle my base cases. So for I in range n plus 1, L I 0 is equal to, well, what did I have here? Li 0 is equal to true, so I'm going to write true. Now for j in range, this is going to be sum plus 1, so b plus 1. What is it going to be? It's going to be L at 0j is equal to false. So now these are my base cases. What I'm going to do now is I'm going to do the main loop. So the main loop, remember, it starts at 1. So for I in range 1 to n plus 1, for j in range 1 to b plus 1, goes all the way to the sum. Now I'm going to check to see if j, and I can just copy whatever I had right over here. If j minus a of I is less than 0, then this means the first case. So Lij is equal to Li minus 1 j. Otherwise, Lij is equal to possibly this, or this. Right. So here I have my elements. So after this, we're essentially done our for loop. Now we're going to check to see if L at what? Remember, what is our ending? Our ending is equal to subsets n and then the sum, so b. So if nb, so if this is true, then what am I going to do? I'm going to essentially print out the subset. So I'm going to start in reverse. Let's say b is equal to the big B, and my set s. Let's just create a list. It can be a set, but I'm just going to create a list. Actually, yeah, let's just create a set. Okay, so while b is greater than 0, now I'm going to check to see if L m minus 1 b, if this is true, then my m is going to be decreased by 1, but I'm not going to add the element. Otherwise, my m is still going to be decreased by 1. I'm going to actually add the element right over here, and I'm going to decrease b by that exact amount, am, and then I'm going to print this. So what am I going to do? Print s, and right over here, let's just do return L n and then num. Let's say we have something like, let's say our a is equal to 3, 34, 4, 12, 5, 2, and let's say we have sum is equal to 51. Let's say b is equal to 51. Now let's say subset sum a b, and let's just call this x, and then I'll just print x. Okay, ran into just a very small bug, just off by 1 error. This should actually be I minus 1. The reason for that is because eventually when it reaches n, well, obviously we can't query the last one, so then all we have to do is query the one before. Again, we have the same error right over here. This should be minus 1. And that should solve it. This should be a set. Sorry about the errors. Num is not defined. B. And there we go. True. So 34 plus 12 plus 5 is indeed equal to 51. Let's try something like 1. Obviously we can't do it right now, so it's going to return false. Let's try something like 7 or 9. Then it's going to give 4, 5. Alright, thanks for watching.